Hi. So in this video, I'm going to talk about Adstock, which is a very important concept in marketing mix modeling. It's one of the media variable transformations that is absolutely central to the way marketing mix modeling is done. But even if you're not doing MMM, Adstock is still a very important concept. And somehow marketers are intuitively already aware of this. So suppose you're spending, and this is the central concept. Suppose you're spending $100 today, from a channel via Google or Meta or LinkedIn or TikTok or LinkedIn, whatever is the industry, and whatever is the channel that you're spending on. Its effect is not just limited to today, right? So if you spend, suppose, 100 from Google, 100 from Meta, 100 from say television even, so there's going to be a delayed effect, a spillover effect to the coming days and weeks. Now, to what extent that effect will be, and that effect, by the way, is on sales and revenue, right? Your target KPI, your outcome variable. Now, that effect, to what extent it will be there and for how long, that actually has to be determined through modeling, right? Statistical modeling. It's not correct to come up with numbers based on some, random benchmarks out there. There is some truth to those benchmarks. I'm not going to dismiss them entirely, but people there's going to be a lot of content that you will come across which will tell you that, okay, these are the benchmarks. If it lies within that range, this is how much the ad stock really should be. There's no such thing, right? I mean, it varies from case to case. You will have to determine it from modeling. You will have to do something called a parameter recovery, and you'll see that ad stock is basically a mathematical model. It's based on calculus and some linear algebra manipulation, and you will have to derive those parameters. So in front of you, you see a dynamic chart here. This animated chart is showing you the ad stock impulse responses, impulse being ad spend from different channels. We're talking about three channels here in this example: television, search, and social. And you can see that how in case of television, the half life and alpha. So alpha is the main parameter. Okay. That's basically guiding ad stock. So the higher is the alpha, the higher is the half life, and half life is nothing but the the point or the lag period. So on the x-axis you can see lag period here, the point at which the effect of that ad spend basically is halved. Okay, so it's the half, the point at which the saturation effect becomes half, right? Or the ad stock effect rather becomes half. So the alpha, the higher alpha, the higher is the half life, and the higher is going to be the continuation of the effect. So in a sense, this is a retention of the effect of the ad spend of the channels. So you'll see that for different levels of alpha, the curves are shifting, and you'll see that typically, again, this is based on overall experience and sort of anecdotal data or information. But the important point is to note that for different types of media, suppose it's very top level awareness oriented media like say television, the alpha is going to be higher, the half life is going to be higher, and it's going to have a longer effect. So you'll see the blue line eventually has tends to be much flatter, right? That's its potential, because it can have a much longer impact, much more lingering effect, and it's progressively going to become lesser and lesser for channels like social and search. So therefore there's the steepness of the curve increases, as alpha also decreases. So the decay effect and retention, they're kind of opposite concepts here. um, Now let's actually look at the mathematical formulation of it. So it's written as recursion normalized, EWMA. That's nothing but just exponential weighted moving average. There's nothing to be confused about the terms here. This is just notes that you can take forward, take away from, as a sort of an accessory from this video. But if you follow through what I'm going to say, it's not as confusing as all of this math looks like. So first of all, there is a recursive effect in the definition of ad stock. This MT that you see here, this is the definition of ad stock. MT is 1 minus alpha into XT plus alpha into MT minus 1. So MT, that ad stock at time T, is dependent on the ad stock at time T minus 1, MT minus 1. That's the key thing here. XT stands for your ad spend for the specific channel. So you will see that there are two coefficients here. One is alpha and another 1 minus alpha. In fact, it's the same coefficient. One is just 1 minus alpha, and this alpha we saw here as well in the curve itself. So that's the main parameter for ad stock. So This repetitiveness, this dependence on past values of Adstock, is basically how is basically what is meant by the recursive effect. So what does it mean really? It means that if you actually do an algebraic rearrangement, we'll actually see just in a moment, you'll see that the weights look like this. It's 1 minus alpha into alpha to the power k, and we are talking about geometric Adstock here, right? So there are different kinds of Adstocks, but this is the most common kind of Adstock. So in this case, you'll see that the main geometric effect is alpha to the power k, and you basically have something called a normalizing effect. That is what you're actually seeing here, this 1 minus alpha. So if your weights sum up to 1 and you're taking k almost tending towards infinity for many values, you are basically saying that it's going to normalize. Normalization means that the sum of the weights is going to be 1, um, which in turn gives us the convolution form. So if you replace this part now, so if you take a summation of the different values of k here, you get wk x of t minus k, which is your which is your normalized version of the expression for Adstock. So this is the Adstock equation. Wk has to be replaced by this part here. So this is geometric Adstock for you in a nutshell. So you have the normalizing component, and you also have the obvious geometric component, which is given by alpha to the power k. Okay, and alpha, by the way, varies between 0 and 1. And like I said, the higher it goes, the higher is going to be the effect. The higher is going to be the duration of the retention or the effect. The longer it is going to stay, essentially. So here's the derivation. If you're interested, for those a little bit mathematically inclined, if you're interested as to why this 1 minus alpha is still continuing to be here, why this takes this particular format. So mt here, this is the formula that we started off with, as you can see, and this recursive effect now is being used. So we can write alpha into mt minus 1 in using mt minus 2. Similarly, mt minus 2 can be written in the form of using mt minus 3. So you can do this, and you can continue doing this. You can keep substituting. This actually follows very easily if you just replace this part here, and if you continue doing this, you ultimately get this functional form where you get 1 minus alpha to the power k x t minus k, which is the regular part, and then you have another additional part here. Now what happens when remember, we already said that we're going to try and take k to infinity as high number of values as possible, which means that the latter part of this formation here, that actually is not required, we can drop that, which means that we are ending up with this convolution form that we just saw earlier, right? 1 minus alpha to the power k, the normalizing component, the geometric component, and then the ad spend. So the sum total and of the sum product of these essentially gives you the Adstock effect, the Adstock function, and this is ultimately supplied into the equation. Okay, and this is basically proving that your summation of weights is 1, right? Because if you just take a sum over these things, 1 minus alpha is constant, alpha to the power k is the only one that's getting summed here, and by definition, this is going to be 1 minus alpha by 1 minus alpha. Here the sum is 1 over 1 minus alpha, so this cancel out and you get 1. So I know there's a ton of math, but this was just to give you an intuition. And again, I cannot reiterate enough, there's a ton of content out there that says that you can start with any kind of values, or there are some not any type of values, but there are some benchmarks that you can follow. While it's good to keep those in mind, it's always important to follow the specifics of your model. These things can be done through parameter recovery. You can actually understand um, what is going to be the true values, or the values that are going to give you the results which are closest possible to the ground truth. So these are things that you have to develop from, and basically determine and estimate from your models, rather than just assigning them randomly. Now, the other important factor, remember from the graph also, we saw half-life. So this is that, like I said, that period, or that time point, that lag where the effect halves. This is to actually give the shape of the curve, right? I mean, this is where it shows that beyond that point, it's going to start saturating, because, or you can say decaying as well, not really saturating. So alpha to the power h, that actually tells you um, that's basically half, right? So that's the definition. That's how you get your h. So that's how it is related to alpha. And alpha is 2 to the power 1 minus h, and from there, if you take the natural log on either side, you get uh, alpha as this exponential expression here, which includes h. Once again, like I said, if you increase alpha, your half-life is also going to increase. So that's the relationship, and which means that it's going to decay, it's going to saturate, or it's the effect is going to carry on longer, right? So if you look at television here, its half-life is bigger here. This is a dynamic graph, but hope you can catch it, that it's actually going to 12. And that's why if you look at the blue curve here, this has the maximum saturation. It's probably its half-life is not saturation, or rather the half-life is probably more than even 15 lag periods here. For the others, it's probably less, it's definitely lesser than that. So that's just an example again. So you will eventually have to do this from your own modeling. Now let's move on to the next part here. So we have talked about Adstock. We have talked about the mathematics of it. We have talked about its derivation. How does it feature in marketing mix modeling? So in marketing mix modeling, you ultimately have different media variables and non-media variables playing together. There are controls, right, which you want to control for, meaning that they affect both they act like confounders. They affect your input variables as well as your target variables. So you have to control for them, so that you don't end up confounding your actual variables. And then you also ultimately have these different transformations. So how does all of that feature together? This is how it looks like. So you have your ultimate media transform media variable, MCT. So see, now we are getting another sort of parameter here. So that's not exactly a parameter. This is basically to denote that you're talking about the different media channels. So media channel C at time point t, you're getting a summation of over k time periods. And so 1 minus alpha c, alpha k, which this is again the formulation that we already saw for the weights, and then multiplied by the ad spend for that particular channel for t minus k time period. So that's your definition for the channel, and for different media channels. Now this is basically up to the point we have this up to this point we have already discussed. This is basically using Adstock, but what happens next is that it gets fed into something called a response function. um, Now a response function is for saturation is defined like this. So you have the mean, this is basically your revenue, the mean revenue, or you can say this is your revenue, and this gets defined as beta 0, which is an intercept value. And then you have the channel coefficients, and then you have a response function, which actually is a function which takes in as parameter, as you can see, or you can say as an argument, the transform media variable that we saw earlier, right? So this one is actually coming into this FC here, and this can be different. So by the way, Adstock, we have discussed Adstock already, in terms of variation of how Adstock actually varies by varying its parameters. So you can apply different Adstocks to different kinds of media variables, right? Similarly, you can have different kinds of saturation for different types of media variables, and not only that, you can have it differently for different times of the year as well, right? That's very complicated. It's not always required, but the option is there. Okay. And ZT transform here, this stands for some non-media drivers. Okay, so these can be your control variables like price, promotion, seasonality, macroeconomic factors. So the saturation basically gives you your diminishing returns, right? So you just add that layering, that is another second layer of transformation on top of Adstock. There are multiple models. We're not going to go deeply into saturation, but this is just to sort of give you an idea that this is how it all works, just to give you a complete overall picture. So hill curve is there, theta is the hyperparameter of importance here, and m to the power theta by k to the power theta plus m to the power theta. This is the formulation for the hill curve. There's another one which is very closely related, as you can see, Michaelis Menten. I hope I'm pronouncing that right. This is a special case of the hill curve equation, right? So theta when theta is 1, you can see this basically collapses or converges to that equation. Then there's others as well, like box Cox. So these are all different kinds of saturation or diminishing curve patterns here. So gamma here, that's basically called the slope or hill coefficient. That's the main parameter for saturation, as well as, so there's actually also k. K is your half saturation parameter. So there are two parameters in Adstock. There's only one the alpha. In this case, there's gamma here. By the way, these parameters can vary. Like I mean, the letters that you choose, or the symbols that you actually choose to assign these parameters can vary. There are different books and different resources which will show different symbols being used, but ultimately there's only one that's used in the power, in both numerator and denominator, and then there's also the half saturation parameter. So this affects the shape of the curves, right? So if it's very, if you want a smooth concave curve, that's what you feel, that it's basically going to rise. The effect is going to rise, and then it's going to pretty smoothly, and then it's going to have a slow steady growth, and then it's going to saturate. If that's what you think that your media effects is going to be, then you can basically use sigma, gamma equals to 1. It's going to be a smooth concave curve. You can also have an S curve where it actually starts much faster, and then it has a slow start rather, and then a very fast growth, and then saturates. That's your S curve. So different kinds of curves are there, and depending on the kind of curve that's correct, this is something again you have to test from your model itself. Different values of gamma will be there, right? So S shaped is when your gamma is greater than 1, right? Slow start, like I said, sharp increase, and then it flattens. If it's less than 1, then it's more front loaded, you can say. So this just varies, depends on the different kinds of curves that we're talking about, and the requirements will vary accordingly. So hope this was clear. Michaelis Menten being a special case of hill curve. But yeah, my point is that we are just trying to see the bigger picture here. Where does Adstock really feature in? So Adstock is in the context in machine learning parlance is another hyperparameter that you can tune. And once again, I can't reiterate enough, you have to use modeling techniques, you have to use coding, in order to do a hyperparameter sweep, as they say, and then come up with the best hyperparameters that gives you the best model uh, performance metrics. So you can't just assign them randomly. Okay, so don't pay attention to, or sort of ignore those kinds of suggestions which tell you that you can just assign them just as you like. You can do that, but you have to just imagine the amount of manual work that it will take to constantly keep iterating manually, right? So multiple iterations means that you have to, that's computationally very expensive, that's computationally very arduous, and so therefore you have to use coding, or yeah, basically resort to coding. So tuning strategies, there are different kinds of tuning strategies. I won't go to the depth of that, but you can do a trend test split. That is very common. So basically, this is used for, as you can see, CV, that's cross validation. So basically, splitting up the data set into training and test, and sequentially, you'll probably just using the different kinds of methods. Like for instance, you can do you can have different kinds of methods here for cross validation. Either this can be rolling, or it can be forward chaining, it can be different kinds of cross validation techniques are there. Rolling window is there, and based on that, you will basically have your test on which the training data hasn't seen yet, and it will basically apply it on that and see if the parameters are working well in terms of the performance metrics that the model ultimately gives. So if that sounds a little vague, do check out my other videos on marketing mix modeling in my channel, which talk about these things a little bit more in detail. When you see the actual code walkthrough, you'll get a more intuitive understanding. Similarly, if it's a Bayesian model, it will have different other kinds of strategies here. This will be more about the kind of sampling techniques that you will have from your posterior, and also the kind of relationship that you're choosing, the kind of posterior curve that you're also choosing, right? You can put priors as well on the parameters, like say HC and alpha C. So that those are tuning parameters, tuning strategies rather, in the Bayesian context. So from a practical point of view, you will have to take into account there might be collinearity across channels, so it might be hard to separate effects, which is a very good point. So you might go with priors, and constantly test with different kinds of bounds, and use calibration or experiments to sort of feed the information back into your system, and see how that goes. Again, reasonable HL ranges, half-life ranges. This is something that I already spoke about at the start. A lot of people talk about benchmarks, and usually what happens, because television is supposedly the one which will, or video, or OOH, that's outside hoardings, and these are supposed to have longer effects, lingering effects. So that's why half-life tends to be longer. Social comes next, and followed by search, performance, or say even shopping, which are much shorter at stock. But again, something this is something that you really have to determine for yourself from your own models. So contributions, this is again a fundamental part of marketing mix modeling. How much does each channel contribute? So this is nothing but, uh, for each specific channel, it's your coefficient multiplied by that response function that we saw earlier, right, which takes into account the transform media variable. And the total contribution is simply the sum total of contributions across each individual channel. This is the contribution for an individual channel. And then if you move on to marginal ROAS from there, marginal ROAS is probably the most important topic here, because marginal ROAS are most important concept in marketing mix modeling, because from that you can get your, you can actually derive, at the point, or you can actually decide where to put your next dollar in, right? So that's nothing but, the partial differential of your revenue, and this is your media spend. So with respect to media spend, so how much your revenue essentially changes for every unit, every additional unit of spend. And this is at a media level, as you can see. So that's why the C appears here. For each individual channel, you do it separately, of course. And then so naturally that becomes beta C, the first derivative of that response function fc mct. And then you have to take in, this is the chain rule of differentiation. So it becomes del mct by del xct, which, by the way, so if you actually look at the derivation, or if you try to do the derivation, you'll see that only for k equals to 0, right, this has a k component, remember, from the earlier equations that we have seen. If I just jump back here, so there is a k component, as you can see, for this mct, which is the media transform variable. For only for k equals to 0 will you actually have a term that actually contains x, and that's why it ultimately reduces to this formula, this version here, which is equals to the first weight w0, corresponding k equal to 0, and which is 1 minus alpha c. Because for all the other days, right, for k, remember, is the lag. For all the other lag periods, it's actually independent. That's what we saw from the formula as well, right? Say it's independent of the spends of those other days, because this is how it ultimately looks like. So if you go back to our normalized version of the geometric Adstock, so see, for instance, the Adstock is actually, the Adstock weights, in fact, if I look at the weights, so this is how it looks like, right? So this is independent of x, right? So it's 1 minus alpha alpha to the power k. So that's how it is derived. If you want, you can ping me if you want to know a bit more about that. But from a practical MMM point of view, we've already discussed a few points. So better timing, right? So you basically have to also think about when the sales come, or basically the sales cycle. So from that point of view, you have to also consider the kind of ad stock that you should be using. So different businesses will have different kinds of sales timing or sales cycles. Channel comparability, budget reallocation, campaign planning, and calibration, these are all things we have touched upon. Based on the marginal ROAS of different channels, uh, and the saturated curves. So not based on, but rather these will be defined by the kind of ad stock that you choose to have, right? So from the ad stock come all these other steps. Saturation is applied on ad stock media transfer variable, and then you have marginal returns, and your budget allocation decision. So everything comes as next steps. So this is such an important step. It's an early on in the process that you do this. So these are again those steps. This is why I love this Notion notebook that I've created here. This is full of very useful material, so you should dive into it, and try to incorporate it into your understanding and your planning work. These are the formulas at a glance. All of these formulas we have already talked about. A couple of them may be new. The CDF formula here, a mean lag, but yeah, nothing that you should be finding too difficult to follow. In case you do, please do leave a comment, as always. Now let's look at a couple of variations here. So we talked about geometric ad stock so far. geometric or exponential, or this is also called the Koek lag, and this is based on someone who has done some awesome work around this, in a related area, Koek. So it's named after him. This is the recursive formula that we saw, which takes into account, it sort of is like acts like an exponential moving average, weighted moving average. So that's what we saw, right? So this is the normalized part of it, with sum total being 1, the 1 minus alpha, and then there's also the alpha to the power k, which is the geometric component. So this we have already seen. This is monotonically decreasing, and this is relatively simple, stable, and interpretable. So this is the most common kind of decay, and you would expect this is how most channels would behave. But if you think, and again, just as a confirmation, this is how the three different curves look like, right? So you see that half life is 1 here, right, for the yellow one, and half life being 3, right? So basically it's, half of the effect is already over by the first week. That's all it means. So the half of the effect is already over by 3. That's what half life 3 means, and that's the case for with the blue one, right? And you'll see that this is becoming flatter and flatter, right? For the last one, which is half life equal to 6, which is somewhere here, which means that its effect is going to carry on for much longer. Now there's others as well, like say V-Bool Adstock, and that has different types. One is cumulative, and another is the probability distribution function, CDF and PDF. Once again, there's an exponential component here. Once again, there's lambda and k, and you can see for different values of k here, if k is 1, essentially that reduces to exponential. Again, if it's greater than 1, so if I look at the curve here, so if k is greater than 1 here, which is the case suppose with the green one, to see that it peaks pretty, it peaks after a delay, right? And then it sort of decays again, right? So depends on the kind of media channels you're talking about. So if you think that there's a media channel which maybe like YouTube perhaps, you might want to apply a Webull ad stock, right? Because you might think that it's going to take a while for it to really have its full effect, and then it's going to start decaying again, right? Because it's not like television as well. So depends, I mean, or if it's like a very quick promotional top of the funnel but video, and you think that it's going to have like immediate effect, then you probably can take a look at something like, say, this one, say log normal at stock, right? So that's going to have your instant effect, right? And it has a pronounced delayed peak, right? And a heavy tail. So it has a slower decay, right? It has a peak, but the delayed effect here is, it has a, like a very steep curve here, and it has a long heavy tail as well, right? So again, depends on the kind of channel that you're talking about, and we have a gamma version as well. So that they have different mathematical formulations. I'm not going to obviously go into the description of each mathematical equation here, but this was in a nutshell everything about Adstock. um, you're going to, you can do see this a lot if you are dealing with anything having to do with predictive analytics or the effects of media, right? So this is so important in marketing science and marketing effectiveness and marketing measurement. It's a central thing. If you're a marketer who is exposed to it for the first time, do give this video a rewatch if anything was confusing, or go ahead and do searches on any of these topics. Lots of content out there already. Or if you have any specific questions that you want to ask me, please leave in the comments below. Always happy to answer them. But so much for now. Thanks a lot for watching, and I'll see you in the next one.